find the domain of these functions. First one, f of x equal to this. Try to create an understanding here. Now, I'm not asking you to solve it. Don't try to square both sides and do something to it. I'm not asking you to solve it. I'm asking you to just observe it, look at it, and tell me what is allowed for the x's. What can I replace x by and be okay? And there's some little strategies here to use. Anyone give me a start? What would you do first in an attempt to find all those numbers that maybe you can't use? What do you have? I think I had 4 or 5 of these at the test tomorrow. Yes, go for it.
X can't equal positive or negative 2.
Okay, quickly, she's telling me, Professor, down here, this is the difference of squares. She said it perfectly. She says, Professor, you cannot let x be a 2 or a negative 2. That would force that denominator to be a 0. Therefore, I cannot let x be 2 or negative 2. I'll put a comma here. And she's 100% correct. So that's part of the domain. I know now x cannot be those two numbers. Now, does that mean x can be anything else? Or is there another restriction to worry about? Yeah, it's in the square root. What about this up here if this is to be defined for that square root? What must be true for that square root to exist? Go for it.
Greater than 0.
That x subtract 1 had better be
Greater than
that which represents, that inside there had better be positive or it could be 0. You cannot take the square root of negative. And if I go ahead and solve this, with what she gave me, there's another restriction. There's my domain. I'm going to put it in integral notation. I have it in 2 pieces here. The guy in my domain says, please, I'm going to do a visual here, just to see what's going on. One part of the domain says 1, darkened in, and you're allowed to use everything greater than or equal to 1. I'm just visually. That's that one. That's a picture of it. Greater or equal to 1. Now, if I go down and pick up this and place it on the same line, how would you represent x cannot be equal to a 2 or a negative 2? How can I show that x cannot be a 2 or a negative 2? Yes, go for it.
Open circle.
Open circles on those two. So 2 here, negative 2 is down here, and you said perfectly, open circles. That's a picture of your domain. Now, can you write that in integral notation and tell me in integral notation what that visual says? And that's what I want those domains written as. So I'm going to come here, guys. Anyone look at the visual and tell me what is my domain? Just based on what you see. Oh, we got issues. It's going to be a long summer. Yes?
From what I see, is it 0 to infinity?
I don't see a 0 to work with.
No, sorry, I just can't see. Is it 1 to
Go
infinity?
ahead. You want to move over here?
It's 1 to infinity, right?
Okay, 1 through infinity? Now, at first I would think 1 through infinity, but there's a catch. I can't use 2.
Oh, yeah.
2 is open.
So I just can't really see the result from
Yes, go for it.
Would it be bracket 1, comma 2, parentheses, and then union, and then parentheses 2, comma infinity?
There's your mathematician. There you go. Thank you. There's your domain. How can you go wrong? Like I said, I have 3 or 4 of these on the exam tomorrow. You're going to think, do some thinking, break it up and see what can I use, what can I not use. And with this, I think I pretty well explained what happened there, and she gave this to me perfectly. This is your domain. Oh, by the way, did I need to worry about this negative 2 over here? I know it's open, but is it in part of that shading at all? No, I didn't have to worry about it. Thank goodness. Okay, next one. Before I jump into something else. I brought some of these in. looks like this. Beautiful. X times x subtract 2, and that's over x squared subtract 9. And I want this to happen to it. And back, let's do this before I show you anything. This looks like that. That's the function. That's the function right there. No inequality symbol. Now let's go through a rationale, something like I did in that first one, come up with what am I allowed to replace x by? Or is there something out there, if I try to replace x by it, I run into trouble? So guys, help me out here, take a look, give me a start on how would you attempt to find the domain. Yes, I see a hand going up, yes.
I thought 3. If you
I
have
cannot
3
use
tracks,
3.
it wouldn't work.
You know what, I'm gonna do this first. I agree with you. Oh, I've been bragging on you guys, the other teachers, other professors. That right there, factors? Now he's telling me, Professor, x can't be 3. I agree. In fact, I also know x cannot be equal to negative 3. What makes a 0 denominator? So right there's a part of my domain. You cannot let x be plus or minus 3. Now there's the numerator. Should I worry about what's on top there in that numerator? I've got x times x minus 2. You think I should worry about restrictions on this up here? No. There's no square root to worry about up here. I didn't place a square root on this one, like I did that last one. There's no restriction at all to worry about. You may replace x by any number you wish on top. That's good. The only restrictions will come from this right here. That says x cannot be equal to a plus or minus 3. Now be careful. This is a visual again. We're saying this. Negative 3, positive 3 are open. You cannot use those numbers. Well, the question is, what can I use? Anything else? But I can't use those two. So in other words, your domain will be, let's see if this color will show for you guys. All these are okay. These caught between, now this is not sign analysis, guys, it's just a visual. Those are okay. This is okay. Now, can someone tell me now that visual there staring at me, what in interval notation could I say is my domain? Who has an idea? Go for it. Go for it.
Okay, yeah. So would it be negative infinity
Okay.
to negative 3?
Well, hang on. I'm good. One more.
And then we have a union. Negative 3 to 3.
Beautiful.
And then union to b to infinity.
Look at that. Done. There's your domain in interval notation. I did visual for you to sort of get that response, and he gave you the correct response. You're done. I'll throw you one more, that you have some of these on the exam tomorrow. We'll call this h of x. And it looks like this. We'll throw a square root in. Square root x squared plus 9. Nothing else, just square root x squared plus 9. Where I know and you know by this time, if you see a square root, be careful. I need to be careful. This, on the Vatican, must be that, because that square root is not defined. That part underneath there has got to be positive or 0. I can't do a square root on negative. Hey guys, if that's true, give me some input. What's my domain? What am I allowed to replace x by? Go for it. Anything. Johnson, thank you. I'm going to replace x by any number I wish. Is it a negative number, Professor? Yes, if I put a negative number there and I square it, it becomes positive. Then add 9, more positive. As long as underneath there stays positive, I'm good. Does anyone see a number I can replace x by here and crunch it out and I get a negative underneath there? No way. So this is going to work for all numbers. So my domain here would be, Johnson tells me all numbers. Now I know that's this. In interval notation, I like, who's saying that? Everything works. Michael?
On the test will be, we have to show both of those?
I'm gonna play it in my direction, I'll tell you which one, and I use interval notation. If I don't say do it, you can do it either way. Okay? Now guys, those are types of values I think we were talking about right at the end of class, yesterday. Any concerns here? Yes, go ahead.
Maybe kind of a dumb question, but like, if it's a square root x squared minus 9, it's a perfect
We
square.
got issues, but hang on, this was done. He says, professor, so it's supposed to be this.
Oh, no, I just meant like, can we
No,
get rid of this?
I'm glad you brought this up, I thought you were gonna help me out. Yeah, now, what's the issue now? That x squared subtract 9, am I guaranteed now I can replace x by any number I wish and I always get a positive underneath there? No, if I replace x by, let's say 1. 1 squared is 1, 1 subtract 9 gives me a negative, negative 8, I can't deal with the negative 8. So this one would have restrictions. Now, I'm not gonna work it out fully, but I'm glad you brought it up. If that had been the case, guys, you're doing this. If that had been the case. Then you do what, factor? Difference of squares. And then I'm not gonna finish it up, then you go into what? Sign analysis. To see what happens here. Should I go and finish it up? Maybe I should finish it up. I'm glad you brought that up. Guys, so if this has been changed, here it is. Now you said, professor, I see all the factoring, I see why it must be greater than or equal to 0. Sign analysis, guys, since we discussed sign analysis and I got sign analysis on the exam. My critical numbers, I hope you see right quickly, are -3 and +3. Are they to be included or open, or one included, one open? What's going on? Should I darken both of them?
Yes.
Yeah, I see an equals mark there. So it could be equal to, and then these are the types where you guys show me, when I ask for it, what number you select. I'm glad you brought this up before I leave this. Let's try -5 maybe. Try 0. Let's try maybe a 6 out there, and here we go, I'm going right here. I'm going to test my signs. Replacing by -5, -5 subtract 3, that's a -8. -5 plus 3, that's a -2. A negative times a negative is positive. Now, is that what I was looking for? That says you've discovered part of your domain. All that works. 0 I'm testing, right here. 0 subtract 3 gives me a negative. 0 plus 3 gives me a positive. That's a negative, and that is not what I'm looking for here. 6 subtract 3 gives me a positive. 6 plus 3 is 9, positive. Get positive all together. And again, am I looking for that? That says yes, so therefore all this gets to be shaded. There's your domain. Now, how does that look in interval notation? If that had been the case, easily done. -infinity up to, what was that, -3? Bracket. Union, bracket. 3 through infinity. Your classmates just helped you out. Make sense? So that's my little recap on domain. How to find the domain, how to find the domain, how to find the domain. I see a hand going up, yes.
For the x squared minus 9 has to be greater than or equal to 0, instead of factoring, could we say x squared, or the square root of x squared has to be greater than or equal to plus minus the square root of 9?
Oh, Lord.
Like, can we do that too?
I know what you wanna do, you wanna do this.
Yes.
And then do a square root on each side.
Yeah. Can we do that?
Done,
Don't do that, okay.
done. But I'm sure you're gonna confuse yourself if you do. Better go ahead and use that factoring and the sign analysis. Yeah, I realize this makes sense, you can move the 9 over, there's nothing wrong with that 9 being moved over. And you could do a square root on each side if you wish. But you may do a square root and say, well, square root of 9 is 3, and then all of a sudden you leave out -3. So I would not do that, I'd factor, go ahead.
Okay. If on a test or exam we do the square root and we say plus minus the square root, would that be accepted, or should we only do factoring?
It's a factor.
Oh,
stay with that square root because it's on each side. Okay, guys, any concerns here? Anything at all? I think that's a sort of a good recap, guys. So this is sort of where we stopped yesterday, I think, wasn't it? Okay, now part 2. Now I've got issues with information. Did I give you guys a handout with what I call parent graphs, some of the functions and their graphs? Just basic graphs that you should know moving into any math course. You should know those shapes. Well, I've got clever students in class. They email me. And one of my students emailed me, and I'll respond to your email if you send it to me. He says, Professor, I see that one that you didn't have on that handout. I don't think I had it on the handout. And it was identified as INT. I don't think I had INT on there for one mine, did I? No, usually I'll stay away from it. I'll show you what it looks like. It's a strange one. Okay, so those basic functions, and then I'll show you another function here shortly here. Remind me though, I'm not going to go through all those I went through yesterday. Did we at least get a chance yesterday, it was all going on yesterday, did we at least get a chance to see what that basic function square root x looks like graphed? Right, I think we did look at it. And guys, you could always plot points like we did back in Algebra 1, but if you have the handout, if you see a square root x function, that's what that look like in picture form. What does the graph look like? That would tell me more about it. Well, that looks like, if you look at the handout, I think, something like that. Is that true? We look at that. I think I gave you the domain and the range on this. So that's one of those on the handout. I'm not going to do all of them. B, please tell me though, on that handout, did we at least have this? Just the absolute value of x. Do we see that one? And its basic shape is a V-shaped graph, like this. And if I place that graph on there, it's going to be like a V shape, like this. Graph. There's your absolute value x graph. And I think we listed the domain and the range on it also yesterday. So there's some others on that handout. Now before I leave this one, I want to jump into the one my student emailed me about. It is in your textbook, the one he's asking about. But I didn't have it on this handout. And you'll see why for a reason. Guys, this absolute value graph. Can someone give me a rationale why, when you graph it, is the graph always above the x-axis? Michael?
The absolute value is positive.
That's the second one I want to hear. The absolute value always comes up to be a positive. It's got to be above the x-axis. That's where I recognize positive, above the x-axis. Beautiful. This one, square root x, because I chose these two, why is that square root x graph? Looks like a half of a sideways parabola. Why is it above the x-axis? And I guarantee if you do a square root, let's say square root 9, is square root 9, if you see the square root symbol, is square root 9 3? Now don't walk out here and say it's plus and minus. I think we had that discussion the first day. Square root 9 is 3. Square root 25 is 5. They all come up to be positive. That's why that graph over there for square roots above the x-axis. Okay, that's this location. Now the one my student emailed me about. Oh my goodness, here we go. He says, Professor, they use initials INT. I've seen this symbol also used to represent this function you have not seen yet. Bracket, x inside, like that. Not a square root, not the straight bars for absolute value, brackets. They call it INT. Whoa, wait till you see what it looks like. And some may have done some research, and you must have done some research and saw that. Guys, on the graph here, the sake of my student, I will describe what we do here, and we're going to start crafting this and see what this strange thing looks like. Now, why INT? Why not CVS? CVS? Why not? Does anyone think they know in mathematics what the INT may be representing? It's the initials for something. Not CVS of the drugstore. Yes,
Intercept.
tell me again.
Intercept.
Not intercept. I love that though. Not intercept. It's another math that I'm looking for. Yes,
Integer?
tell me again.
Integer?
Integrals?
No.
Integer.
Oh, intervals?
Integer.
Oh,
G or Z.
integers,
Yeah,
integers.
yeah.
That's exactly what it means. INT means integers in mathematics. Now here's the problem before I start cracking the strange graph and it's requested. Does anyone recall what is an integer? Or maybe I should throw some numbers at you and ask you, are these integers? If I throw 4 at you, and say, is 4, from what you know, is 4 classified as an integer? I hope so. How about -4? How about 0?
Yeah.
How about square root of 16? That,
We don't have
yeah,
this.
but that's 4.
Yeah, that's 4.
1/2?
No.
No. -2/3? No. No fractions. Just nice, well-behaved numbers. I can have -10. Would that be classified as an integer? And since that set is so large, we usually identify it with that symbol in math. And then I'll classify the numbers here. This is a large set of numbers that looks something like this. Anything discovered in that set is an integer. Those are nice, well-behaved numbers. No fractions, no decimals, no pi. Pi is not an integer. Okay? Now, what does that have to do with this graph? This is, well, place some numbers in here and find the greatest integer function. So to get that graph and see what this strange graph is going to look like, I'm going to do it today. Try it for you. I suppose I use my notation for greatest integer, and in there I place 1/2. Now inside there you may replace any number you wish. But coming out must be one of these. That's the restriction. The greatest integer function, just integer itself, must be one of those nice, well-behaved numbers in that set. But inside there it's open. You may put anything at all inside there. But make sure coming out is one of those numbers up there in that set. Now you said, Professor, 1/2's not in that set. Of course it's not. Yeah, I'll do this though. It's caught right here between 0 and 1. Is that true? Now here's what we do. Talking about strange. You look back at your set of integers and ask yourself, what's the closest one I can get to 1/2 and not go over? Which one of those in black there is closest to 1/2 and does not exceed 1/2? What's the closest in this case?
0.
0. Look at this. We'll try another one here. Suppose inside here, I place, since it's open inside, maybe a 3/8, a fraction. You say, Professor, 3/8 is not in that set up there. I know it's not. I know though, I think, is it also caught between 0 and 1? So what must you say is the closest in those black? Closest number you can get to 3/8 and not go over, not exceed. Still 0. Now I'm trying another one here. If I place inside there this, 2 itself, is 2 in there already? So what do you think the greatest integer function's value at 2 would be? 2 itself. That's the way it works. Now we'll try another one here. Just get an idea. Let's try, I'm going to call it 5/2. 2.5, which is not there. Now, I know where it's located, 2.5 is caught between. 2.5 here. 2 and 3. So which of those in the black, the integers, can you get closer to it? Choose 2. That's the answer. Try just a couple more, and then we'll start scrapping this, see what makes, what sense we make of this. Guys, we'll try this. Be careful. I will try -1/2, which is not in that set. It shouldn't be. It's not an integer, but I know it's located right here. Is that true? Now be careful. Of those black integers, which one is it closest to -1/2 and not exceed? -1. And finally, one more, and then we'll see what happens here. 3.14, 3.14, of course, not in there, so the closer you get to it is, I heard, 3. That's the way it works. Now, what on earth does it look like, though, thinking like this? What does that look like when I go back to the grid to get a graph? Is it gonna be a circle? Is it gonna be a parabola? Is it gonna be one of these other graphs you've already seen? No. It's gonna be one of the strangest graphs you've ever seen up to this point. Okay, so let me plot this first and we'll take questions here. Guys, I'm gonna label my axis. Just get ready for it. Now, I think this is what makes sense through my description here. Why the graph takes this shape here short. So I did a few numbers there. I'm gonna start at 0. The greatest integer value at 0, since 0 is in there already, is what? 0. Is that true? I'll start here. You say, well, Professor, this is on the graph. I know for sure. 1/2, we tried 1/2 earlier, I think. Was 1/2 also at 0? I think also I tried what, 3/8? Was that 0? That tells me all these are staying at 0 until I reach 1. Now what's the greatest integer function value at 1? I don't think I tried 1. Since 1's already in that set, what's the answer? 1. It jumped up to 1 now. It's up here. Not here. It's open now. It jumped. Now if I tried like 1 and 1/2, I may have tried 1 and 1/2 back there. If I tried 1 and 1/2, guys, what's the greatest integer function value at 1 and 1/2? 1. So this one will stay on this little stamp, we'll call it, at 1 until I reach 2. And the 2 jumps up to 2. There's a pattern here. Then you go from 2 to 3. And another jump. Now let's try it on the other end, on the left, on the negative. This is going to be open. Watch what's going to happen here. This is going to be darkened in. And another little step to show what's happening over there. Looks like this. And those little steps continue forever. Sometimes textbooks call this the step function. This one uses int, integer function. Greatest integer function, step function. I thought it would be clever for you guys to look at it. Let's see what happens here. We did. Okay? Now, can someone help me out? I'm gonna list the domain range on this. Can anyone tell me, based on my description here, here's X, that's what domain is. What am I allowed to put inside the brackets, or inside there? It's open, isn't it? In fact, I tried different numbers myself. It's open. So here it's all real numbers. Or if you wish, it's this. Now, I need a clever response now for the range. What's the up and down? What are the y values? I tell you, there's a simple answer, but I think maybe you're overlooking it. Yes?
Integers.
It's a set of integers. Right here, this one stays at -1. And -1's up there in the black set of integers. This one stayed at 0. 0's up there. 1, that's an integer. 2, that's an integer. So the range is gonna be the set of integers. I'm gonna just use this symbol if you don't mind, to represent the set of integers. This is your range. All these numbers would be the range. And that's your domain. Who was it emailed me last night? At midnight. And asked me that. I thought, gee, midnight? Yeah, I responded. Okay, yeah. So I think you were interested in that. Now you see what's going on? Is that I and T?
I think so, yeah.
Yeah. Okay. So guys, some basic graphs here. So that's going to lead me up to where really we are. We'll get ready for. I hope I got room on the side right here. Just see, wait now, Professor. How about some other graphs that may not be as well behaved? They don't look as cute as these do. They may look a little crazy on us. And I don't have any of those on that handout. Well, that's what it's going to come down to. Here we go. Just do a little separation over here on the side. Let's draw a graph. I'll give you a description. You guys, I think, have one drawn for you on the handout I gave you. Guys, will make mine for my example right quickly. I'm going to do something like this. And I think I'm going to put a close point there. Please tell me, did you see anything like that on the handout of the parent graphs that I gave you? The handout that contained this and some of the others I gave you yesterday, did anyone see one that looked like that? No, it's not that. It's not considered one of the parent graphs, but it is a graph. Is it the graph of a function? Would it pass the vertical line test? Yeah. Yes. So this is representing some function. I didn't name the function for you, but I know it's some function. I'm going to do this also labeled to my x-axis and y-axis. You guys can see it to work with. Okay, let me step back and look at this as a function. Listen and watch carefully. We're going to read these graphs from left to right. I'm going to say this point right here, which is closed in. I'm going to say this point represents, I want to say over -2. Let's say down 4. That point right there. Its coordinates are out. -2 on the grid, down 4. Need not worry about this one. This is forever. As I read from left to right, here we go. And we travel, and we stay on that graph, we stay on the curve. From left to right, am I first increasing? Am I rising on that graph as I do that much there? As I start at the beginning, the initial, and start moving toward the right, is it going up? It moves up, so they call that in calculus, this piece is increasing. Increasing. Then all of a sudden, I notice at the top there, that's where it stopped. Comes stationary. And then all of a sudden, when I stop, what's going to happen is, in my travel, I then start falling. Down to that point. The word being used now in mathematics to show that part's dropping is that piece that I have, like in this color, is decreasing. Now, is my travel done? No, I have one more piece there to get to on the end over there, and it looks like it's going to, let's just put it in black here, pick up here, and see if you guys will agree, this is another rising, increasing portion. Did you guys agree? From left to right, rises, falls, rises again. As I go back and take a look at my travel here on that curve, I notice up here, looks like it reaches a peak. A point there. But more than likely it stops, or I stop, and I continue my travels, I'll start dropping down. this point, please tell me, is that a high point in that particular vicinity? Okay, I'm gonna call it a maximum. Let me ask you this though, listen to my vocabulary. It is a maximum. Now tell me though, if you look at the entire graph, not just that little vicinity, if you look at the entire graph, is that the highest point on the entire graph? No, because the entire graph does what? It goes forever. But in this little vicinity here, a little locality where I'm located, it is the maximum height, isn't it? So they identified this as a local maximum. That's a local maximum point. Now, someone tell me before I go through my travels here, what would be a good way for you as a good, clever student to see whether or not you have a local maximum based on what you see right now? What would be a good way to test? Let's say I name the function for you. You don't see the graph. You don't have the graph in front of you. I ask you the name of the function, and I ask you where is the local maximum, or what's the maximum value of this function, local? What would be a good way for you to test to see where's my local maximum located? And the graph's not there. You want to see it? Who tell you? Oh, I'm hearing it. Somebody saying something.
Between the increasing and the decreasing.
Okay, to the left of this maximum, right here's my maximum point. In the green's to the left. Was that green part rising? Increasing. Then all of a sudden on the other side of the maximum, which is that orange looking color, was it falling or decreasing? So if it transitions from what? Increasing to decreasing, you're going to have a max. That's going to be a transition from increasing to decreasing. Also, I thought I was saying, I saw a hand going up earlier. Okay? Now, looks like, as I do my travel here, the orange and the black, right here. I bet you probably know what name might be appropriate for that point there. That's a transition point. From the orange to the black, what do you think would be appropriate for a word here to describe this point? There you go. A local minimum. And it looks like I see a transition. On the left, it's falling. On the right, it's rising. So I've got local max, local min, and then we'll go from there and talk about some other type of max and min we could have at certain times. Yes?
If you're listing where the graph increases in interval notation, would you include the local max?
Beautiful, I love that. Love that question. Hang on. Just hang on to that thought. Beautiful. So far, so good, guys? Okay. Now, she's asked the appropriate question. She says, Professor, label a little bit more for me. I see the increasing, decreasing business. I see maybe where that local max should be and that local min should be in those particular localities. That's why they call it local. Okay, here goes. Oh boy. Why not? Let me label that maybe this point right here, that we're going to call the local maximum, this point right here. Let me give coordinates to it. -2, let's say this is -1, comma, let's say it's up 2. And we're going to label this local minimum, just so I can work with it. Let's say it's out 1. Let's say down 5. Out 1, down 5. Now let's start listing things that she wants me to list for her. First, let's see if I have enough here. I do have enough. Can anyone tell me what you think the domain on this entire graph function? From left to right, along the x-axis, that's domain. How would you describe the domain on this graph? From left to right. Where does it start on the left, on the x? And how far out on the right, on the x, does it go? How far out to the left does it go? On the x? -2. Now on the x, how far out to the right, based on what you're looking at here, how far out to the right do you think it's going? It's going through infinity, because this thing's going out, I know it's going up, but it is also going out this way also. So it is, in this case, -2, looks like I'm going to put a bracket on that. Through infinity. range, if I can answer it. The range on the graph is the up and down. So guys, how far down does this graph drop? -5, based on my sample here. How far up does it go? Infinity. -5 through infinity. There's the domain and the range on that sketch. Is that true? And I got other items also, but I have not listed as she wants me to list. Professor, tell me in interval notation, when is that graph increasing? I know you shaded for me, but tell me in interval notation when that's happening. Go ahead.
I know this sounds like a stupid question,
No,
but
no, no,
how do you
no.
get that bracket again?
Because I closed this one in.
Oh, yeah.
If it's closed in, you use a bracket. Okay? Now, this in interval notation, if we can. Where is my graph increasing? Well, I've already shaded for you. I told you where it's increasing from left to right. It's increasing, I think, right here on the green. Now, here goes. This is her question. Can anyone tell me in interval notation, when is that taking place? What do you think would be appropriate to tell someone, when is that green taking place? I see it shaded, but when is it taking place? Go for it.
-2 to -1.
Thank you.
And then is it?
Hang on. I know exactly what you asked. -2 to a -1. Is that true? Now, you might be wondering, should I put a bracket?
I think you need a union.
Okay, well, I'm not quite finished yet. But that little piece right there, should I put a bracket on that -2 or a bracket on 1? Right here? I know some textbooks do. Tell me why, should I put a bracket on there? Is this point right here, this point, is it increasing or is that just the initial point? That's just the initial point. I'm going to put everything in parentheses. Okay, so it's rising from -2 over to a -1. In fact, even at -1 is doing nothing. I mean, was it -1? Yeah. At -1 is not increasing, it's just stopped. Did it? Just stop there. It starts falling. And you tell me there's another increasing. Okay, union. And the other increasing was, I think, in the black here, was it?
It's 1.
Was this from what? 1 through?
1 through infinity.
Infinity. There's your increasing. Okay, decreasing in interval notation. Guys, I labeled it in the orange there, it's falling, and I would describe that as falling from -1 to what? +1, was it? It's falling. So we got increasing, decreasing, local max, local min, domain, range. Now your textbook says also have students to realize that sometimes you have something known as, and here goes. Yes, go ahead.
Do you only use the x values for increasing and decreasing?
Oh, you mean when you describe that in interval notation?
Yeah.
Ah, I got you. Yes, you do. You just use the x values. And they use intervals. The other part that I'll close down with here with the domain, we got domain, range, local max, local min. They also want you to identify, before you go to calculus, sometimes, and who knows, I may have here, but we'll see, the graph may have what is known as an absolute max. Why do you think they use the word absolute and not local? What do you think they're asking you to find on that graph if they use the word absolute max? Where's the absolute max? What's the highest point of all points? On the entire graph, is there a point highest on this graph? There's not. There's not. We've already said it goes forever. I can't say infinity. Infinity is not a number. They want a number. What's the highest number this graph goes up to? The highest max. There's none. Goes forever. Maybe there's one of these. Yeah, we'll see. The absolute minimum point. Guys, if I look at the entire graph, is this point right here the lowest point I see? Yeah. Okay? Now, usually they just want the y value. But if you list the entire point, I'm happy. I'll give you full credit. And in fact, the y value is what? -5? So we're just saying -5 is the lowest it drops. Okay? They usually put a -5 as the y. If you guys do this, I definitely would go ahead and give you credit. You want to name the entire point. Okay, local max, local min, absolute max, absolute min, it's not that hard. Increasing, decreasing, we should be ready for this. Mr. Park, we need all this, don't we? Arena? Yeah, we're in those higher math courses, we need this. Guys, any concerns here? At all? Okay? I'm trying to think though. Does someone have a handout where I had the graph drawn for you? I had a sample, I think, on one side of a handout, I think. A large graph, it's drawn for you, something like this, probably. Oh, I see it right here. Like this. Something like this. And it was just for practice, something much like what I'm doing here. Something like that. To go through and see if you could identify these items for us. Okay, I didn't place the answers here. Mr. Park, did you send out the answers?
Yeah, but I did one wrong. Yeah, but it's a yeah, sorry.
Okay. But he sent out the answers. You did one wrong.
Yeah.
Okay. So guys, it's much like what I did here. Domain range, I'm just continuing with my graph over here, guys. You can do this for a little practice on yourself there. Someone read the parts to me. We're not going to answer the one on your handout. I'm going to do it with my practice problem. Can someone read what was being asked on that particular problem? What was number one? What did they ask you to name for number one? Oh, domain range? Well, we got that done. Right here it is. Same thing. Except you got a new graph to look at. Okay? A little practice. What was next? Yes?
F of -5 equals. So
Oh,
is it a point?
Got you. Now here I can say, well, since I have a different graph, I can say, well, what is f of a -1? Do I have enough on that grid or graph to show at -1 what its partner is? And here's -1 squared over what?
2.
2, and that's the answer. F of a -1 is 2. I see it right there, paired up on the graph. Therefore, you can easily answer yours. What's next?
Half of another point.
Oh, another
Okay,
point?
3.
Yeah, guys, same thing. Just search and find it. It should be on that graph. Just name it. Very easy. Here's something else.
On what intervals is f of x increasing?
Beautiful. Got it out of the way. We should now be able to answer yours. And probably decreasing. Okay, what was after that?
On what intervals is f of x less than 0?
Oh, now I have not answered that up here. Okay, on what intervals is, I'm going over here, guys, is my graph, my function, this. Not increasing, not decreasing, they can use those words. Where is f of x less than 0? Someone in this clever class tell me. What would you do if you have just the graph to stare at? I didn't name the function for you. When is your function guaranteed to be negative? Now, tell me what you would look at on the graph to answer that. Go for it.
Parenthesis, -7 through.
Okay, now do it on mine up here,
Oh,
if I can.
here, let's see. From -2 to, and this is just for x values, so from -2.
Oh, got you. Okay, this right here translates into, and they say, where is your function less than 0? You say, Professor, you didn't name the function for me. No, I didn't. I showed you its graph. Translate is, where's that graph below the x-axis? When it's below the x-axis, that means your function is negative. So you're down in negative territory. So guys, please tell me, is this piece right here, little piece right there, is that little piece right there below the x-axis? That's one part. Of course, I'll need to answer though, to label this point for you. Which I did not need it at the time. Let's say this is, what do we call it, -3. Now, did you label that for me? You know what, maybe -1 would be better. I used -1 already. Gee. The -2 here, what do you wanna call that, -1 1/2? Let's say the intercept is -1 1/2. Now, how would you label that? When is it below? From -2 to where? -1 1/2, if it were labeled like that.
Bracket,
Beautiful, why would I not?
wooden bracket, the -2.
Beautiful, why would I probably not?
It's just as
I just see less than 0, not less than or equal to.
But the negative.
I got you say, but Professor, this is included, I see exactly your argument, you say, good, Professor, could I even do this? Jonathan, I think about that.
Yeah.
Love it, leave it. That kind of either way, absolutely. In fact, it is below, that -2 is below there. Now, is there another piece of this graph that's also below, besides that little piece there that I just shaded? Is this below? All this. On my graph, is all that right there below the x-axis? So that's another answer, I gotta put union or comma. To show there's another piece of the answer. Guys, I didn't label that for you here, and -1, let's call this -1/2. See what's going on here, and that was 1, let's say that right there, it's 2. Intercepts. Now, how would you label there, when is it below, when is it negative? From what to what? Is that from what, -1/2? Over to where? I label this 2. So this is when this is happening. Whoops, I'll get ready for this. That's another piece of this. This is -1/2. And Jonathan, I'm thinking about you here. -1/2 over to what? 2. Is that little piece also below? Now, why would I not for sure put a bracket on? I wouldn't. On the -1/2 or the 2. Where's the -1/2 located? Is it right on the x-axis? Is it below? It's right on it, so that's equal to 0, it's not less than 0. And on the other end, I think I placed a 2. Where's 2 located? Is that right on the x-axis? Then I'm not gonna put a bracket there. Now guys, the other one, f of x is greater than 0, where's it positive? Well, I've done so much marking up here, I hope you guys can see all this. It is positive above the x-axis, please tell me, is this, oh boy, is all that right there, guys, above the x-axis? And tell me, when is that happening? From negative, what was it, 1 1/2? Over to, I think, did I label this number here for you or not? Oh boy. Or did I call it -1/2? Yeah, so -1 1/2 over to -1/2. It's above, from here to here, it's above the x-axis. Is it above the x-axis somewhere else? Is this little piece here also above? And how would you describe that? I think I label it as a 2. What would be a good way to describe that? Union what? 2 through infinity. Wow. Let's calculus. But there's more. There's more. Does it make sense though? With that increasing, decreasing, local max, local min, absolute max, absolute min? When you look at a graph, who would think? There was so much there on that graph that you have to identify. Okay? Now, I gotta watch my time here. Beautiful. Let me take a breath. Are we okay at this point? Making sense. So tomorrow, if you have a graph drawn for you, I'll supply the graph. And I'll have it marked. Could you answer these questions? Domain, range, local max, local min, absolute max, increasing, decreasing, like we did on this one. And if you want to practice with, you can practice with this one. And Mr. Parker says he sent the answers out, but I think he made a correction on one of his.
It's like bigger than 0, I think. But,
Did you let them know though?
not yet.
Oh, okay.
Okay, I'll send it out today. Yeah.
Make sure.
Okay.
Now let's do the part, next part. We should make more racist, I like that down there. It would be so nice if SMC would say, Ramsey, score your students only on participation. Base their grade only on participation. At this point right now, I think almost every student in this classroom would have an A. Darn it. Wouldn't it be nice? Please grade my students on participation. Are they attending class, Professor? Yeah, I'm taking attendance today, but they're here. Well, give them a grade. Are they participating in class, or do they have their heads down sleeping? No, they're not gonna sleep in my class. No, they're alert. Okay, they're alert, and they're responding. Wouldn't it be nice? They want to walk out with an A. And you grade for math 7, you grade for calculus. Wouldn't that be wonderful? Is it gonna happen? No. But that would be so nice if it would happen. Coming up, let's go back to a graph. Get ready for this. I'm going to show you here. I think a good way to approach this with you is I even stand here. Here we go. Let me make my graph somewhat like I did. You know what? Let's do this. Make it look like this. And I'm going to have one very rough look at. Now we'll call this the graph of some function. It passes a vertical line test, just a function. I did not label anything for you. I didn't give you any numbers to work with. I do know, based on what we just did, is this point right here, if I had labeled it for you, is that a local min?
Yeah.
Local minimum? And there's a local max there. And also, is that graph from left to right increasing at certain spots and decreasing at certain spots? Well, just like that over there. You said, Professor, we're going to do it differently. I gotta do this to show you something else on that handout. I'm gonna label a point for you. Here we go. I'm gonna place a point right here. And I'm gonna label its coordinates. Think of a good way to label it. Not numbers. We use numbers over there, out there. I'm just in general. Just label the coordinate. I'm gonna use an X and an F of X. For the coordinates of that point. No numbers work with this time, just X, F of X, or X, Y, just in general. Now I'd like to label also, let me use this color here. Let's say a point that's right, oh my goodness, let's say right here on that graph, on that function. I'd like to label it also, not with specific numbers, but just in general. Now, how am I going to do that? Well, you can say, Professor, you can just use different letters, different variables. You can do that. But what I want, though, to make this connected to calculus is this point right here that I have, it looks like in orange, this point right here, is it definitely different than this point over here? And we definitely have different coordinates? Guess what they do in calculus to show that's just in general? They say if you call the first one X, or the X coordinate, you know the one on the other side there is different. So label it is, they'd like to do label it with this, X plus H, where that H shows the difference. They put an H there, just to show that point is different than the first one. Now, can someone be clever and tell me what would the Y coordinate look like? On my first point, it was F of X. What do you think it is for the new point, where they have labeled the second point as X plus H? What do you think the second point, the coordinate, the Y coordinate, would be? That's it, hang one up, yes. Love it. F of X plus H. So X, F of X, and then X plus H to show that point over there is different, and then she gave that answer to me perfectly. F of X plus H would be a perfect label element. Now, please tell me, here goes. As I travel from left to right on this graph, you know, this falls, it's decreasing down to that local min, we know that. And then it rises from that point on up until I reach my destination. It's what they're interested in calculus as you travel from one point to another on a graph. Guess what calculus is based on? As you travel from one point to another on a graph, guess what they're interested in you discovering? Any idea? Go for it.
Maybe like the distance between each point?
Well, distance, you could find distance, something else. I'll give you a hint. At first, we were falling. Then we transitioned into what? Rising. Is that a change? Rate of change. They will know the rate of change as you travel from one point to another on a graph. Therefore, I need to come up with a way to come up with the rate of change as you travel from one point to the other. Now, before I get back to my graph, I want to ask you this. Let's go back to middle school. Did you guys enjoy middle school? Yeah. Well, I hope you did. You're out now. Did you have fun back then? Yeah. Middle school, elementary school. Elementary school. You guys took math in elementary school. You remember that? Everything was so nice in elementary school. Gee. I used to supervise student teachers, not walk into high schools, sit back and observe them, and critique them on their style of teaching before they become full-time teachers. Well, there's all kinds of things going on. Good things and bad things. Oh, yeah, it's fun though. Now, let's go back. Why not? Let's go back to, let's say, middle school. Let's see if this blue marker will hold up for me. Let's say my travel, my curve, I'll call it curve, my travel consisted merely of this. Wasn't going up and down, local max, local min, it's just, my travel just was straight line. Which is a function. Now, tell me from middle school, guess what you were asked to do back then? When they were concerned about it, I doubt the teacher used this phrase. If they were concerned about the average rate of change as you travel from here to your destination here, and you went in a straight line, and they asked you for the rate of change. Guess what you did back then? To find it, but they probably used a different vocabulary word. Be smart.
Slope.
Slope. They asked you to find slope. Now, I don't know whether you recall what slope was back then as you traveled from one point to another on a straight line. I think you might recognize, though, I'm gonna write mine as letter M representing slope back then. And I think the formula is something like this: y1 subtract y2 over x1 subtract x2. And some teachers may even say that was rise of a run. Some even expressed it like this: delta y, change in y, over change in x. Some may have even introduced that delta there. Delta y, delta x, change in y, change in x. And you found that, and you didn't realize, and I doubt that teacher said that's the rate of change. They probably just said slope. They were happy back then if you used to find a slope. They said, go ahead and use that formula to find slope. See what the slope is. Is the slope 1/2? Is the slope -2? What's the slope? That would be considered rate of change. Now I need rate of change on this one. It's a curve. You didn't see this in middle school. But they're asking again, what's the rate of change now from this point to this point, except this time they're not in a straight line. They're on a curve. Well, guys, what you're asked us to do is connect them with a straight line. Connect these two. You know what? Maybe connect these. 2 points with a straight line. And, oh boy, here it goes. Now, do I have 2 points on a line? Could I now, like I did back in middle school, I had 2 points here. Could I now apply the slope formula? And express the slope of the line connecting those 2 points. That would be a good way to come up with the rate of change as I travel from one point to the other. Now, here's the issue. If I go back to middle school, changing y or changing x, the slope, that's rate of change. And I should here, my orange point, my blue point, express the best you can what it looks like if you express the slope by the slope formula, which is right here. For middle school, use that formula based on this representation and tell me, and I'd like to label so it makes it look nice. We label what points for you besides what you see right here. Yeah, why not? Let's let this be the x1 point from middle school, which is f of x1. And this one is the x2, f of x2. Let's label it. Now, if someone tell me, based on the way my slope formula is written from middle school, what would y1 subtract y2 look like on this curve? Or on that line it connects. What am I letting y1? This is y1 here, guys. x1, f of x1. What would y1 look like?
Parentheses x plus 8.
Okay, thank you. Oh, I got you. Right here. Hang on. Hang on. Jeez. Label like this. Y2. This is my x1. This is my y1. The slope formula from middle school says take y1 subtract y2. y1, like he's telling me, is f of x plus h. Guys, let me squeeze this down here. F of x plus h. Subtract from middle school f of x, which was what? Y2? And don't stop there. The slope formula says now take x1 subtract x2. Well, x1 looks like, well, you have it labeled as what? X plus h?
Minus
There you go, right here. Minus what?
x.
X. And then the only thing I can do here with that representation is, look at this. Leave that. I can cancel the x's out in the denominator. They will cancel. Leaving what?
H.
These will cancel. H. Now you're ready for calculus. You want to do a derivative. I'm not going to do a derivative with you, but you'll be doing derivatives in math 7 based on this. They give a name to this expression we just came up with. They call it a difference quotient. Difference is a difference, I see a subtraction sign. And quotient implies division, it's a division also. They thought difference quotient, and that's where it came from. Now what will that help me find? The rate of change from one point to another on a curve. F of x plus h subtract f of x all over h. Now, here we go. I need your help. And I just know someone will give me the response I'd like to hear. Here we go. I'll give you a function. There's my function. Simple. Linear function. I'd like to find, without a graph, I'd like to find that difference quotient for this function. No graph. Just find the difference quotient. Now I've got to be very careful. Very careful. Can someone tell me, break it up into parts, might f of x plus h look like, no graph, on this function? What does f of x plus h mean to do to begin with for that given function? What did it mean the other day when they gave you a function and asked you to find f of 0, f of -5, f of 4? What'd you do back then? Did you just plug it in or substitute it in? Is that true, guys? If you ask you to find f of something, what do you think it's going to look like here if I go to my function up here and do as I'm supposed to do? Yes, go for it.
Replace the x in 2x minus 5 with x plus h.
X plus h right there. You substitute x with x plus h. If I do, that's going to look like this. I'll put it in a different color to show it goes in. That. Subtract 5. Now that, and block it off, that represents that. And that difference quotient formula that we have over there. That's f of x plus h. Everyone agree? Just go to my function, replace x, substitute x with x plus h. That's the way the function now looks. Don't stop there, it says now subtract. Here we go. Now it says on the end, subtract this. In that formula. Well, what's that? That's the original function. You say repeat it, subtract it. And don't stop there, it's all over h. Well, we did it over here, we saw where it came from. It's h. At this point, that's what it looks like for this particular function. Now let's clean it up. If I try to clean this up, step 2, I see a distributive property staring at me. It's 2x plus how much? 2h. Subtract 5. And then down here, I see by a distributive property with that negative sign, is that negative 2x plus 5? All over what was it? H. Do we agree? Can I simplify further? Yeah, I think I see some terms that might cancel out. I think the 2x's are gone. Will the 5's cancel? So that leaves me what? 2h over h. And guess what else happens? The h's will cancel. Leaving me an answer of, are you kidding? 2. I didn't graph this for you. Can someone tell me it's a linear function? Can someone tell me if I had taken the time to graph it? Would this have graphed into a straight line? Something like a straight line. For 2x subtract 5 graphed into a nice straight line. And even better, to close down this with this one sample here. Does this take the form of way back in middle school? Remember mx plus b? Is that what my original black function given to me? Is that the form it takes? mx plus b. What's the m representing? What's the slope here? What do we get? Slope. The difference quotient corresponds with slope. You find the difference quotient, you're talking about slope. Right there it is. Matches up. Now, before we take a break here shortly, let's see if my time won't be coming up real quickly. You said, Professor, what else will they ask you to do here? They want you now also to close this down. And we'll try some more difference quotients as we get back to the break. We don't have a quiz tonight, do we? Okay, no quiz. Okay. You see the line that connects these 2 points? So for now, please ask you to write the equation of the line that connects those 2 points for all this to happen. Now let me step back and see if I've given you enough to work with here. Hang on. The line that connects the 2 points, well, my goodness, is my function in my first example, is it a line to begin with? Is that true? That is the line. Now though, I may wait till I can break through this one. Sometimes it'll be a curve like this, not a straight line to begin with. And you have to write the equation of the line that connects the 2 points. This one you're okay on this, right here though. Guys, everyone see a connection between slope and, difference quotient? So I got a difference quotient on the test tomorrow. You say, oh, professor, you showed it to us today. No, it's not gonna be hard. You can find a difference quotient, my goodness. And I'm here at, 2 o'clock tomorrow for a session to help you out. You always know what this is. We'll practice with this more after the break. How to find the difference quotient. How to find the difference quotient. By the way, guys, before I take Michael's question. If, please tell me. Let's say I gave you that function. And I asked the question is, what's the difference quotient value for that function in the blue? Could you quickly say, Professor, I'm not gonna work it out again. I'm not gonna work it out like you did here, using this, formula. No. Jonathan says, Professor, it's -3/2. Automatically. Is that the slope? Is that L max plus B? Is that true, guys? Okay, and then I'll answer Michael's question. Now, please tell me before we take a break. Can you as easily tell me now what the answer is? No. What happened? It's not linear. It's what now? Quadratic. So there's still a way to find the difference quotient, but you're not gonna be able to tell me the answer right quickly like you would for a linear. Okay? Michael, go ahead.
What was my question?
Oh, that was the question. Okay, absolutely. So if it's x squared, x cubed, some crazy function up here, it's gonna require some work. And I got some on the handout for you after the break. If it's linear, my goodness, the answer's right there. Always staring at you. It's a slope. Guys, any concerns here? If you guys move on to Math 7, you're not at the top of the class. I know all these professors. They know me. I know them. And we talk. You think you talk? You should hear professors talk. Or maybe you should not hear professors talk. We talk. Randy, did you have so-and-so in your Math 2 class? Yeah. How's she doing? What? Oh, really? Then normally say, Francie, your classes, you seem pretty good, solid students in Math 7, prepared. I have a student of yours. How's that student doing? Top. There it's the top. Wow. Now the one who said, something's happening, guess what I do? Since they know me here, I ask them, at what time do you have that class? With that student in it, would you mind if I have time, could I just step through the door? And I did this once, and the chairs were turned so this student, my former student, didn't realize I was there. So I just sort of slipped through the door, and I stood behind the desk for a while. And the other student was sort of laughing a little bit. He didn't know what was going on. He didn't see me behind me. And he turned around and said, you know, Professor Range, what are you doing here? I'm checking on you. I heard you did not do too well in that first quiz. I had to call you out. So guys, don't mess up, because I'm gonna find you. Find you, see what's going on here. Okay, I think there's one more question. Was there another question? Okay, guys, let's go ahead and take a break. Take your 15-minute break. We'll come back, get all this finished up.